and today's talk is going to be about accelerated Apache Spark on Tanzu and VMware Cloud. So what you'll hear about from us today is coming together of two important technologies, the Apache Spark technology and the VMware with Tanzu technology, or Kubernetes. You're going to be hearing a lot about Kubernetes in this talk. I'm Justin Murray, from Solutions Architect in the Cloud Platform Business Unit at VMware, and I'll let my colleague Mohan introduce himself here.
Yeah, I'm Mohan Poteri. I'm a Solutions Architect in the Cloud Services BU. I and Justin collaborate on a lot of projects, and we focus on AI, ML, and data processing platforms. And so this talk is based on our work, the work we did on Apache Spark 3. Go ahead, Justin.
Thanks, Mohan. So I wanted to set the context first for what Spark actually does and why it's important for you to know about it. And this chart includes two important areas, the area of data processing and the area of machine learning. Data processing is largely that leftmost column there, where it may be the case that the end user simply wants to do decision support or analytics or data cleansing, data preparation, SQL or SQL type work is very dominant there. And Spark has really taken a big lead in that world, even becoming the new big data platform for doing that, for data preparation, decision support, and that type of thing. And the SQL engine inside Spark has really won a lot of acclaim for doing that. But Spark is not just for data analysis and data preparation. Since last year, when NVIDIA announced GPU support in Spark, now it's being positioned into the mainstream machine learning world, so that Spark is becoming support infrastructure for training your model, that's training your machine learning model. And we're going to see one of those called XGBOOST later on. And also for actually executing your scoring or your inference part of machine learning. So we're covering two areas today, the area of data analysis, data processing, that's the left-hand side there, creating data, preparing data, doing SQL actions on data, doing decision support on it. And also we'll be talking about machine learning on Spark as a platform. And that's pretty new, that machine learning should be run on Spark. But what Spark has to offer is a distributed platform for doing machine learning in a distributed fashion. And we'll see more about that as we go forward. So what does a pipeline look like that includes Spark? And this is a classic machine learning pipeline. But as you see, the left-hand side of this is largely about data analysis, data cleansing, data visualization, data transformation. And that's where Spark has really won. In fact, I think it's displaced Hadoop in combination with Kubernetes. It's pretty much displaced Hadoop as the platform to do your big data analysis on, your preparation of your data, your queries. And you might do that based on a data store like PostgreSQL or S3 or many other modern data platforms. And Spark is excellent at this, but it's also now being used a lot for model training, model deployment, and even in applications. So it's a general platform for these two areas, is what the point is here. And it's become very popular in modern data science environments. And the combination of Spark and Kubernetes together is a very powerful platform. And that's what we'll be using principally throughout this talk. So why would a data scientist or a person doing a lot of SQL work like Spark in particular? Well, it's easy to use from the languages that they like Java, Scala, and Python. Spark grew up out of the Java and Scala work, and those two are very close to each other. And the Python language is pretty dominant in data science. So having interfaces to those languages makes Spark immediately attractive to data science. It's also a very general platform. It can combine SQL analysis, which are maybe executed in batch, with streaming data and complex analytics. You can do pretty powerful stuff. We're paying attention mainly to our left-hand column here, but on the right-hand column, you can see the number of different algorithms that Spark has to support machine learning. We're not going to go into those in detail today. We'll talk about one of them, which is called gradient boosted trees there in detail later. Spark is highly performant. It's much it's won a lot of battles against the older big data Hadoop world in the performance area. And, companies who sell Spark actually pride themselves on performance and optimizing performance. And there's been a lot of attention paid to optimizing SQL as well to make SQL run very fast on Spark. And Spark also runs everywhere, runs on Kubernetes, runs on top of Hadoop, runs standalone, and runs in the cloud. So it's a sort of universal distributed application platform, which makes it very attractive for people doing data analytics or machine learning. So one of the innovations that's come to Spark over the past year or so, especially since version 3 came out, is GPU support. And GPUs are commonly used on VMware, and there are at least 2 methods or maybe 3 methods of using GPUs on VMware. We're going to see 2 methods in use here in this talk. One is direct path IO and the other is NVIDIA vGPU. And these are different, but only subtly different. Direct path IO, as you see here within the virtual machine, I've got my application. That's where Spark lives. Underneath that is CUDA and the drivers. You don't need to worry about that actually, because Spark allows you to set these up fairly easily. You can set them up yourself, but there are methods now of setting them up for you. And then you have your guest operating system, and in direct path IO, any CUDA instructions that the application would be admitting to use a GPU are passed through the hypervisor directly to the device. And as you can see, the device could be a GPU, an ASIC, or an FPGA in the direct path IO method. In the vGPU method, we're virtualizing a GPU. We're presenting a virtual GPU to our guest operating system. We're doing that via the NVIDIA vGPU host driver, which is loaded into ESX. And there is a specific guest driver as well. These 2 must be matched up. But essentially, your virtual machine now can either consume all of a GPU or a portion, a share of a GPU. And that's called a vGPU. And there is a method of doing that in time sliced mode, which is the traditional vGPU way, or there's a method of doing this in strict isolation mode, which is called multi-instance GPUs. That's a new thing with the A100 GPU that came out recently. And that allows you to separate one virtual machine from another in a more isolated fashion, giving more predictable performance. And we've used both of these here, and you'll see them later on in our demos in action. How do I assign a GPU to a VM? Well, it's pretty simple. I go into Edit Settings, add a new PCI device, and then I'm presented with a series of profiles or a set of choices in the green box on the right here. I can choose Direct Path IO, Dynamic Direct Path IO, and NVIDIA vGPU there. And you see I've chosen for my profile an NVIDIA vGPU profile, which happens to be an A100. That's their latest, with 20 gigs of memory. That's the 20C, and the C is a computer profile, a machine learning profile, so that not much graphics is going to be done in this. It's purely executing a neural network or XGBOOST or some such machine learning thing. So setting up a GPU is not hard for the system administrator in VMware. And we can say a lot more about that, and you can find a lot more material about it offline from this event here. But GPUs are core to what we're doing in this talk. So we've done a lot of testing of Spark with Kubernetes over the past few years. You may have seen papers from our colleague Dave Jaffe from Performance Engineering on this, and he wrote quite a lot on this. But Spark and Kubernetes have matured since this first thought came out. And now there is something called the Kubernetes operator for Spark. An operator is a Kubernetes term indicating not just installation help from Kubernetes, but also runtime help from Kubernetes for driving any such platform such as Spark or Kafka or many other things have an operator for them now. Database technologies have operators. And so what an operator does is allows Spark to participate in pods, and pods are the unit of execution on Kubernetes. They're a collection of containers. and it manages the health and the life cycle of that collection over time for you. So it's literally like a human operator. It's monitoring the health and managing that health for you. And what you do to start this up is fairly simple. As you can see, there's a tool at the bottom of the screen called Helm. This is a Kubernetes tool for installing and configuring various things on Kubernetes. You add Spark to your repository on Helm, and then Helm install that operator, and you're pretty much up and running with the Spark Kubernetes operator. And this comes from Google, where Kubernetes came from as well. And this is a new style of using Spark on Kubernetes. It's the second style that we've seen over the past year or so. I'll mention the first style as well, which does all this by hand, where you the end user, would have to set this all up by hand. But eventually what you get is the Kubernetes scheduler in the red box at the top there is managing your Spark pods, your driver pod, and your executor pods. And executors is where the real work is done in Spark. That's what executes in Java or Scala to carry out the job that you're going to give it. That's the Spark operator for Kubernetes, and that's an important component of what we're going to be showing you as we go forward. And that's running on VMware, of course. Previous to that Spark operator, you had to set up your own executor pods, your own driver pods, load them into Kubernetes, and typically you would set up a pod per virtual machine, and the Spark driver would be in a virtual machine of its own. But the operator takes care of all this for you now. You still have the Kubernetes scheduler on the left-hand side, scheduler and an API server. Those are the control plane for Kubernetes. Those are set up when you set up Kubernetes. And instead of doing a Spark submit to that scheduler, as we did in the older method, we now do a kubectl apply -f file name, which is the way in which we make any change to our Kubernetes system. And what we're doing there is creating a Spark object. That Spark application object will execute on the pods. So that's the older method. There was some advice from the performance papers on Kubernetes here. That advice is still relevant if you're using the older non-Spark operator method of deploying Spark on Kubernetes. You can still do that. This advice is less applicable now if you choose to use the Spark operator, because it will take care of a lot of these background steps for you. I just included this here for completeness in case you haven't adopted the Spark operator quite yet. Okay, I'm going to pass over to Mohan now to talk about his section. So I'll stop sharing.
Thank you, Justin. So I'm going to share my screen now. And I'm going to go to presentation. All right. So now we're going to see how Apache Spark 3 is deployed on top of VMware Cloud Foundation. We will first introduce VMware Cloud Foundation and its capabilities, then look at the components of the solution, then we go into the use cases. So VMware Cloud Foundation 4 is a truly hybrid cloud platform that accelerates development of modern apps, and also automates the deployment and lifecycle management of complex Kubernetes environments. It provides IT operations admins complete visibility and control to all the aspects of compute, network, storage infrastructure resources. And at the same time, it provides developers frictionless access to the developer environments and also the infrastructure resources through their own services. So both the IT admin and the developer are able to interact with this infrastructure through that VCF provides. So that's kind of what, if you look at the VMware Cloud Foundation Services provides, it provides Kubernetes with the RESTful API. So they're abstracted into these sets of services. And the hybrid infrastructure services are abstracted from the virtual infrastructure, and container resources can be run on top of it. And then the Tanzu runtime services delivers what we call the Kubernetes that developers are able to use in the environment.
Okay, so now that we've introduced how Tanzu runs on top of VMware Cloud Foundation, we will now move on to the building blocks of the solution. So here, what we had in our lab was multiple server nodes, Dell R740 servers, each with NVIDIA Tesla T4 GPUs. The platform we use is VMware Cloud Foundation 4 with vSphere 7. We have a TKG 1.2.1 with Kubernetes version 1.18 as our Kubernetes version. So we are leveraging the following software as well: Apache Spark 301 with NVIDIA CUDA 10.2. We will be using Spark Rapids 2.12 and XGBOOST. So Spark, these are the two use cases: the Rapids and the XGBOOST, and we'll kind of describe them in the future. And then we also have a high performance networking with Mellanox, and also 10 to 25 gigabit Ethernet switches. And we have NFS storage and fiber channel SAN. The fiber channel SAN is for boot disks, and NFS storage is for sharing data between all the pods. So if you look at our environment, here you see the cluster. We have a resource pool for Apache Spark. We have the top node, the 40 is actually a master node. And then we have 8 worker nodes as seen. So these are all running Ubuntu 18.x. And then each of these worker nodes, the 41 through 48, have a GPU card in them. So if you can see this next slide, you can see, if I look at one of the worker node profiles, you can see that it has got its own PCI device, which is a Tesla T4 NVIDIA processor. So every worker node has a GPU that can be leveraged by the pod running on it. So now let's move on to the use cases. So Justin had gone through the capabilities of Apache Spark, right? And the Apache Spark has evolved over time from primarily being data processing to now also doing machine learning. So we are going to have two use cases. Apache Spark is very good with SQL, and so we want to do NVIDIA Rapids, which is NVIDIA's acceleration of processing that works with Spark. And we will validate the Spark performance with TPCDS, which is a common verification methodology. We will look at some of the query performance. We'll compare the query performance with CPU-only worker nodes versus CPU plus GPU worker nodes. So that way we can see, since Spark 3 now supports GPUs, we want to see how the data processing works with GPUs, right? And so we want to do that comparison. Then we have machine learning with XGBOOST. So we're going to leverage some mortgage data from Fannie Mae, Freddie Mac. Then we're going to use that to train a model, and then we're going to test the model. So we'll look at these things in more detail now. So Rapids, right? The Rapids suite of software is built on top of CUDA. It gives you the freedom to execute end-to-end data science analytical pipelines entirely on GPUs. It relies on NVIDIA CUDA primitives to low-level optimization and exposes the GPU parallelism, the high bandwidth memory that's available with GPUs through a user-friendly Python interface. Rapids also focus on common data preparation tasks for analytics and data science. So in the past, you would have heard of GPUs for accelerating mostly machine learning, right? And here in this case, we're actually, the Rapids is focusing on actually accelerating data preparation and analytics, which is quite a big chunk of the data processing platform. And so it uses a familiar data frame API. Rapids also includes supports for multi-node, multi-GPU deployments. And it uses Apache Arrow data structures in its GPU data frame. The GPU data frame batches of column variables from multiple records take advantage of the modern GPU design, and this accelerates reading, queries, and writing. So this is kind of what Rapids does. And so that will be our first use case. In the second use case, we'll be using a well-known gradient boosted decision tree called XGBOOST to use for tackle regression, classification, and ranking problems, right? And it is written in C++ and CUDA with wrappers for Python and R. XGBoost now provides a seamless drop-in GPU acceleration. So that's kind of what you see in the picture. You see XGBoost there, and it's actually be able to leverage GPU acceleration. So that will be the second use case we will look at. So the first use case is data processing. The second use case is training. So now let's look at NVIDIA Rapids. In this use case, we're going to do NVIDIA Rapids with Apache Spark 3, and we're going to validate it with a subset of TPC-DS queries. Spark and other components needed are deployed, and then approximately 1 terabyte of data has been generated to run TPC-DS against the data. And the subset of the TPC-DS queries are then executed on CPU, followed by GPU, and then we will compare them. What are the deployment steps? So we installed Spark operator for Kubernetes. Justin had gone over what the Spark operator for Kubernetes does. Where Spark itself is a distributed application, and now we are combining Spark's capabilities with Kubernetes by leveraging the Spark operator. The Spark operator can execute Kubernetes tasks on top of Kubernetes. Okay. So then what we do is we install the Spark history server. The Spark history server is used to view the logs of either already finished or currently running Spark applications. So it's required part of ability to monitor and get metrics from all our runs, right? And then we create a custom Docker image on NVIDIA CUDA with Ubuntu 18.04 that incorporates CUDA, UCX, Spark, CUDF, and Spark Rapids. So all these components are installed and then incorporated into the container. So it's all inbuilt into the container. And then we need a repository to store the container images, and and then we leverage Harbor, which is an open source repository, similar to the Docker repository, but it can be privately hosted. And it is a VMware product that VMware bought and built and then open sourced out. Now, after that, what we do is we run a bunch of queries to generate a 1 terabyte data set for running TPC-DS. We store the data in what we call a Parquet format. This is a compressed, optimized format for querying. And but last but not the least, we configure the Kubernetes worker nodes for running GPUs. So the Kubernetes worker nodes can run either on CPU only or can run on CPU and GPU together. And then last but not the least, we will run the query testing. So this kind of shows you our Harbor repository, a screenshot of the Harbor repository and the 2 images that we have. One of them is for Rapids and the other one is for XGBoost. And here, each worker node has its own dedicated NVIDIA T4 GPU. And here you are seeing that we are actually have the plugin so that we can enable the worker nodes to access the GPUs. So we have the NVIDIA device plugin shown here. And you see all the 8 nodes out there, each of them having their own plugin, right? So now, based on this, what we did was we ran a subset of queries. We want to do the queries that matter. There are 99 queries in TPC-DS, and we wanted to kind of focus on a subset that is important for data processing and analysis. So this is the subset that we have. So we ran a select set of TPC-DS queries in both CPU and GPU mode. The GPU mode uses the Rapids accelerator and the unified communication UCX. And the UCX provides a optimized communication layer for message passing libraries and RPC data. And it also uses high-speed network for inter-network communication. So we leveraged, and we did the GPU run, we leveraged both Rapids and UCX. In the CPU mode, we use something called adaptive query execution. So TPC-DS queries were run using 1 terabyte of data, which is in Parquet format. The comparative runtimes of these queries are now shown in the table. The results show that for longer running transactions, in most instances, the GPUs accelerate performance, right? GPUs are new to the querying field, right? GPUs have been mostly used primarily for machine learning in the past. So here is the first time we have a foray of GPUs into data processing. And we do see good acceleration in many areas that require a lot of time. Short running transactions, because of the startup and startup times and closure times, the GPU doesn't necessarily make a difference. But for the longer running transactions, the GPU certainly does make a difference. Right? So now, before we go, we'll go into the Rapids demo. So I'm gonna switch to a video, and the video will play its own audio because it is a lot of material that's covered, and it's better to have the audio on the video because it's much faster, right? So I'm gonna end the show here, and then I'm gonna play the video.
VMware Cloud Foundation 4 now natively supports Kubernetes with vSphere 7 with Tanzu Kubernetes Grid. VMware Cloud Foundation with Tanzu is a hybrid cloud platform that accelerates development of modern applications, that automates the deployment and lifecycle management of complex Kubernetes environments. VMware Cloud Foundation provides runtime services, automation and infrastructure services, all delivered via Kubernetes and RESTful API. Spark is the de facto unified engine for data processing, data science, machine learning, and analytics workload. Apache Spark 3 offers enhanced support for Kubernetes with the Spark operator. It also provides GPU support with pod-level isolation for executors, which makes scheduling more flexible on a cluster with GPUs. The solution leverages Spark History Server that is used for metrics and performance analysis of the completed Spark applications. NVIDIA RAPIDS suite of software libraries, built on CUDA, provides the freedom to execute end-to-end data science and analytics pipelines entirely on GPUs. It exposes that GPU parallelism and high bandwidth memory speed through user-friendly Python interfaces. It includes support for multi-node, multi-GPU deployments, enabling vastly accelerated processing and training on much larger dataset sizes. The following use case was validated for Apache Spark 3, TPC-DS with NVIDIA RAPIDS. We executed TPC-DS queries using Spark operator on Tanzu Kubernetes cluster, TKG, and incorporating NVIDIA GPU. Validated Spark performance with Tanzu and NVIDIA GPU, leveraging Rapids. We generated 1 terabyte of TPC-DS data. We convert the data to Parquet format. Here we can monitor the conversion application through Spark UI. This is the Docker file used to create an image to run conversion and TPC-DS queries. We are using Spark 3, UCX, and Spark Rapids in this image. This is the YAML file that uses Spark operator to run conversion to Parquet format. Here we use 1 driver and 6 instances of executor. We are using this template YAML file to run TPC-DS queries on GPU. These are the UCX configuration parameters for Spark. Here you can see that we are using one driver and 8 instances of executor. We are using this template YAML file to run TPCDS queries on CPU. This is the CPU run of the TPCDS query. We can see that the 8 executors are launched by the driver. Note that the query is now complete. We are now running a TPCDS query on GPU. The query run is now complete. We can see the Spark UI shows a completed task. Here we can see the GPU and CPU run on Spark History Server. We ran TPCDS for a subset of queries. The comparative run times of these queries are shown here. The result shows that for longer running queries, the GPU accelerates performance. As we can see, GPU makes a significant improvement for the queries Q6 and Q64. In conclusion,
We'll look at conclusion later, so I'll move back to the presentation. So next we will look at the GPU accelerated machine learning with XGBoost. In this use case, we use an example mortgage application to demonstrate Rapids AI GPU accelerated XGBoost Spark project. An example mortgage application was used to demonstrate the efficacy of this XGBoost. The mortgage data is publicly available in the Fannie Mae and Fannie Mae website. The data we use for this is years 2000 and 2001. And the solution requirements, we're using Apache Spark 3. We need NVIDIA GPU, which is a Pascal or higher, multi-node clusters with the identical GPU configuration, Ubuntu 16.04 or higher, CUDA 10.1 or higher, NVIDIA GPU compatible with CUDA, and then the Nickel 247. And so we have all of this incorporated into our Tanzu environment. The environment that we use for the Rapids works here as well because we had all these components. And then the steps here again are pretty similar. We create a Docker image to run the XGBoost related tasks. We fetch the mortgage data and store it. We build a scalar distribution file, jar file for machine learning. And then we perform ETL conversion of the mortgage data. So this is called typical data conversion process. Then you run a mortgage ML training, leveraging XGBoost, and then you test the trained model. So now I'm going to turn it over to my colleague, Justin, to actually do a demo of this solution.
Thank you, Mohan. Thank you. I'm just going to share my screen here. And you should be seeing my vSphere console now, the vSphere client on your screen, which will show us the lab in which Mohan was executing his work and the XGBoost work as well. So this is the collection of 8 servers here. Set this in motion. And on each of those servers, you'll see that there was a T4 GPU. This could be any type of GPU here, but it so happened that we had T4s available, and also some Mellanox ConnectX.
I don't see you sharing, Justin.
Oh, I'm sorry. Okay, so here we are. Hopefully you see it now.
Yeah.
Yeah, so you're seeing the ConnectX technology here and the GPUs. And if we look inside one of the virtual machines, such as QW41 here, there are 8 virtual machines in total, and we edit settings on them. You'll see that this has a particular GPU, in this case, a Tesla T4 in pass-through mode. We'll also see an experiment done at NVIDIA, in fact, on the same type of data with A100s in vGPU mode later on in this section. So what we're doing first is testing the acceleration that we get just from the GPU alone, and then we'll add some networking acceleration into this one. And this is another VM with the same Tesla T4 in pass-through mode. As I said, we'll do vGPUs next after this. So what we have here is an 8-node Spark cluster. Each node is made up of a VM. And notice here the tabular nature of the data. This is important because a lot of machine learning demos you'll see use image data, but this is data with rows and columns in. Here's our driver file. This is just to confirm that we are on the right version of Spark and the right version of the Spark operator here. That's the name of our application, Spark Train Mortgage GPU there. The type of data, as Mohan mentioned, is going to be Parquet, and the version of Spark is 3.01. Parquet, as he said, is an optimized form of data storage for queries to execute. And we did a lot of SQL queries in preparing this data. And you'll see here that when we execute the training mechanism, we're just executing against 4 of the 8 available executors. So we're not using the entire power of this cluster here, but you'll see the results are quite impressive. And that little line there, kubectl apply -f, is the application startup in Kubernetes. So that spoke to the Kubernetes and executed these 3 pods. That pod called the mortgage GPU driver is what we're going to look at next now to see what the logs are of that pod, a pod being a collection of containers in Kubernetes. And here's the logs. Some of this data is standard Spark stuff. What's happening now is the training error is being analyzed as we go along, and the training error is going down over time, which is a good thing. We want the minimal error we can get. And our training is now completed, and I speeded this up so that it consumes less time. Elapsed time for the training here was 97 seconds, about 1.5 minutes or so. And we can see that our pod, Spark Train Mortgage GPU driver, has indeed completed. The job worked fine. When we did exactly the same training on a CPU-based system, we got 1,994 seconds, which is about 30 minutes, about 16 to 20 times slower on just a CPU-based system than it was when accelerated using a GPU. So the GPU did this a power of good, but there is still room for improvement here. So looking around inside the Spark history server and the Spark console now, we're looking for where the time is being spent. And of course, it's being spent in XGBOOST, which is our machine learning training model. But where exactly is the data being shuffled from one executor to another is of interest to us. And data shuffling is the process of sending data from one GPU to another over the network, which can be a time-consuming process. So we'd like to speed that up as well. This is our environment in Spark here. This is all Spark console standard stuff here. You can see our executors have executed correctly with no failed tasks here. And one of those executors has done an awful lot of shuffle, spent a lot of time in shuffle. So we'd like to improve that if we can. So now we move to another environment in which we have a different setup here. We have both GPUs and NICs at the same time. And these NICs are set up to do GPU direct RDMA. Again, we have a Spark 8-node cluster, but this time our GPU is an A100 from the latest Ampere family, and the networking is the Mellanox ConnectX-6 technology. So this is the code that executes in XGBoost here. It's simply training on tabular data, very similar to the tabular data we were using earlier. And the results from this show that we get about a 31x boost over the CPU form. So not only do we get a 20x boost from the GPU, but we get a further 2 to 3x boost from the networking that we saw here. So using these technologies in concert, GPU to accelerate machine learning and GPU direct RDMA to accelerate the networking gives us a tremendous boost here of performance from 30 seconds down to less than 2 seconds. Okay, so that's our XGBoost demo. Let's minimize that. And go back here to our slides. Okay, so that was XGBoost, and XGBoost is hugely popular because...
Justin.
Sorry, share again. Okay, thanks.
You need to swap to the other screen.
Okay. Okay. So as Mohan explained, XGBoost is hugely popular among data science people. It's been known to win performance competitions that are set up so that different teams compete against each other and try to achieve the highest accuracy in the shortest time. XGBoost became very famous as a result of winning several of those. And it's very popular for manipulating tabular data in machine learning today. Okay, so what we saw there was Spark 3 with NVIDIA GPUs, Ubuntu, CUDA, and Kubernetes all combined together into one solution. And I was going in the wrong direction there. So our conclusion is VMware Cloud Foundation, as you saw from Mohan, is a great platform for Apache Spark 3 and for machine learning and decision support running on top of Spark 3, actually. VMware support for GPUs and Kubernetes can be effectively used with Spark 3, as you saw. The TPCDS, which is the industry standard benchmark for decision support with NVIDIA RAPIDS and GPUs, effectively showcased acceleration of SQL queries against data from the mortgage and from other sources here. And we used NVIDIA GPUs with Kubernetes for machine learning with XGBoost in the final section here. So two very different application areas. Apache Spark is applicable to both, and GPUs can accelerate both. So that's our presentation. We'll take some time now for questions in the chat and Q&A.
Great. Thank you very much, Justin. And thanks for the demo. That was really good. As we look at the conclusion, Justin, there's a comment in the chat about getting your slide deck. So if you wouldn't mind sending that to me, I'd be happy to post it for our partners for playback.
Sure.
And then as we wait for questions to come in, I know you're thinking about this as we conclude today. So to our partners, as we wrap up, if you have questions for Justin or Mohan, you can always email me. Just put in the top the subject of the VM Live session and tell me it's for Mohan and Justin, and I'll forward those questions to them. But you can email me at vmlive@vmware.com. Like I said, we know you think about these after the session, so don't worry about being lost without us. We're here and we're going to stay here to help you. Mohan, let's go back to you as we wrap up. Any key takeaways you want, or any last minute thoughts you want to leave our partners with?
Yeah, just like we concluded, right? So here, what we showed you is the latest and greatest data processing platform needs the latest and greatest in infrastructure. And that's kind of what the VMware Cloud Foundation provides. We support GPUs, we support acceleration for networking, and all these capabilities are leveraged in an excellent manner and helps accelerate these workloads like we showed in our presentation and our demo. So I just want partners to take away that we are the leading infrastructure platform, and all new and upcoming applications would run well on our VMware Cloud Foundation.